Okay, so if the nucleus changes, that would qualify as a nuclear decay. And what you end up having is a proton number change. It literally transmutes from one atom into another. And so your potassium will transmute, or we talked about it earlier. Your carbon will transmute, just depends on what the situation is. Any kind of radioactive decay is a changing of the number of protons. And on the periodic table, when you hit 83 protons, bismuth, nothing that has more than 83 protons is stable. That doesn't mean that it won't be around for a long time, but it definitely means that it will at some point in the future go radioactive. So do you guys have a periodic table? Okay. You need the other side. Yeah. So there's one that says half-lives. On that backside, look at the legend, find half-life. And then it'll show little numbers like, look at uranium. It should say something like 10 to the 9th billion or 10 to the 9th years. Maybe 4.5, 10 to the 9th years. Bottom.
There we go. Okay.
Yeah, I think you're on the wrong side.
Here now, 4.5 E.
Okay, 4.5 E and then 9.
Yeah.
Okay, so that'll be around for 4.5 billion years. That's what its half-life is. And we'll be more specific about what what half-life means. But just because it's radioactive doesn't mean that it can't be around for a long time. But then you could look at something else like, how long is AT around for? It's next to radon on the list. So 85 underneath iodine on the right, column number 17 on the bottom. What's its half-life? 8.1 hours. So, I mean, the planet is obviously more than an hour, 8 hours old. So there isn't any of it left. So when we were talking about the halogens, we talked about fluorine, chlorine, bromine, and iodine. And then when we got to acetine, I'm like, don't worry about it. There's like a teaspoon of it on the whole planet. And why is there only a teaspoon of it on the whole planet? Because any element that has more than 83 protons is radioactive no matter what its situation. That does not mean that there are atoms with less than 83 protons that are radioactive. They are. So you can have less than 83 and be radioactive, but every isotope over 83 is radioactive. There are no non-radioactive isotopes if you've got more than 83 protons. We really wish we knew what 83 was about. Why 83 is the number, but we're not there yet. What? It's just too big. I mean, ultimately that could be the answer, that it's literally just too big. Because I mean, what is the nucleus? This tight packing of subatomic particles, protons and neutrons. And now you've got 83 of them packed in, and maybe 84 is that's it. Now there's too many, because as I pack these positively charged things in, they're trying to push away from each other. The neutrons are buffering that, but the nuclear force, which is the strongest of all the fundamental forces in the universe, but it only acts over like micron distances. If you get any further away, then it's like super strong, but I can't reach out very far. And that's the issue. Maybe the nucleus has exceeded the nuclear force's ability to do its thing. Okay. Say again. Right. Yeah. Why the nuclear force is just such a short radius. Okay, so these are not chemical reactions. These are nuclear reactions. A plutonium the size of my backpack could power the United States for 10 years. If that was pure plutonium or pure uranium-235, maybe not the whole United States. Definitely Oregon for a friggin' 100 years. But the power level difference between electrons and protons is they're not in the same scope. It's Wilt Chamberlain playing basketball against kindergartners. Like Kindergartners are never going to score. Wilt's going to score 500 points. It's only going to be capped by the amount of time it takes him to run down the court kind of situation. All right, so why radioactive? So that's what we've been talking about. The nucleus ends up being too large for its size, can't hold itself together. I mean, my only problem with that explanation is we talked about copper. It was a long time ago, but we talked about when we were talking about isotopes, the copper isotopes. Let me pull that up. All right, so here, Wikipedia page for the known isotopes of copper. The smallest copper that we know of has a total mass of 55. So you can see that the Z number, 29, the Z number is the proton number. So it's 29 all the way down the list. And then the N number is the neutron number. So 26 neutrons is not enough. And so this guy has a half-life of, milliseconds, seconds, minutes, hours. So the issue that I have with it's just about the size of the atom is 29 protons, 34 neutrons, stable, not radioactive. 29 protons, 36 neutrons, stable, not radioactive. But 35 is radioactive. That's not allowed. Why is that not allowed? 34 is fine, 36 is fine, but the one in the middle is not. Like, everybody's radioactive before 34, everybody's radioactive after 36. So why is 35 radioactive? We really like to know the answer to that question. It just doesn't. Yeah. Somebody threw a piece of erector set into a Lego structure and it just doesn't snap together correctly. It doesn't work. And so we're not sure why. So we're going to talk about some types of basic radiation. And first thing I'm going to talk about here is ways to annotate an isotope. We've seen a little bit of this. So there's type 1, type 2, and type 3. Type 1 is type 1 gives you the most information. Type 2 makes an assumption, and type 3 makes a bigger assumption. So what we have is the symbol, and then I've got a mass, and I've got a proton number. So for the first one, that first number on the top, that's your total mass. And then the bottom number is your proton number, and then the C is obviously stands for part. So why is type 2, why does it make sense to do type 2?
So just know the numbers when you see the element.
When I see C, I know it's 6, so I don't need to write 6. So basically, it's just somebody kind of being lazy or then just making an assumption that you understand. So it might say 235U, and then you're supposed to know that it's got 92 protons. Also, you have a periodic table, you can look it up in like 1 second, so it's not that big a deal. So literally, it's just saving some people some time. And then the last one was produced by secretaries. When all this stuff was done, typewriters were kind of a new thing. And so you would write down everything that you got in a notebook, like Grayson's, and then Grayson would hand the thing off to a secretary and she'd type it up. Have any of you used a real typewriter? Can you imagine how difficult it is to manually insert superscripts and subscripts? You have to grab the roller and move it like half a notch, type, and then move it back, write whatever the symbol is, then backspace 3 times and move it down 2, and then type the whatever the number is for the proton number. And eventually they were just like changed it and wrote, instead of writing superscript C, they would write C-12. And then when they would read the paper back after it got typed, they're like, how come this thing changed? Why does it look like this? And they're like, do you want to type that? Okay. That's kind of how that went. So we got this new one because you can type that very easily. So carbon-12 is just written carbon-12. Uranium-235 is U-235. But we still have some uses for the other stuff, especially the top one. So you might see these things written in these different ways. And the three main types of radiation that we're going to see are alpha decay, beta decay, and gamma decay. So alpha decay is out of the nucleus comes an alpha particle, and an alpha particle is basically the nucleus of a helium atom. The nucleus of a helium atom has a mass of 4, a proton number of 2. So what comes out of the nucleus is 2 protons and 2 neutrons in a nucleus form with no electrons. So it comes out charged. The next one is a beta decay, and a beta is an electron coming out of the nucleus. How is an electron coming out of the nucleus? There's only protons and neutrons in the nucleus. There's a slight mass difference between the proton and the neutron, even though we anequate them both as an AMU number of 1. How do you think a neutron became neutral? Took a proton and you stick an electron to it. What happens to it? Neutralize their charge, and I got a neutron. So that means that that neutron is really just a proton and an electron stuck to each other. And sometimes the electron comes off, and that neutron then turns into a proton. You okay with that? And then the last one is a gamma decay, and gamma is just light. So the nucleus, its substance doesn't change. It's just that that nucleus is now that it was energetic and needed to release some pent up energy, and so it does, and it comes out as a gamma. And this is usually the way that we X-ray things is we use gamma release or X-ray release from some substance like technetium. And I mean, there's another example of what's going on with the nucleus. So I had said earlier that anything bigger than 83 is radioactive, right? But also look at element number 43 on the table. Is there anything weird about the symbol for element number 43 and element number 61? They're gray. Yeah. That means that there's no known naturally occurring elements of that atom on Earth. So it's 43, 61, and then you can see after uranium, they're all gray. Those ones are because we've made them. Humans made those things. Neptunium, plutonium, americium. But why is 43 not work? So we had said earlier, why is 83 the max? Well, what's wrong with 43 protons? What's wrong with 61 protons? We don't know. We know there's a problem because no elements, we have made both technetium and promethium, and promethium is super short half-life. Technetium, we actually can use that for some scientific investigation because it produces this really high energy gamma, but they don't exist naturally and they just disappear. You can't like contain them, you can't like freeze them or whatever. They will literally just turn into some, they will not be that anymore. And so what do I mean by that? They will not be like, what happens to the technetium? What happens to the promethium? What happens to the plutonium? What do I mean by they're not that anymore?
The list,
What do you mean?
they just go down a proton?
They could go down a proton. They could go up a neutron. They change the proton number is the most important part about it. So if I'm radioactive, for whatever reason I'm radioactive, what it means is I've got a bad ratio of protons to neutrons. So how do I manage that? I could change one of my protons into a neutron. I could shoot out protons and neutrons to try to make my number smaller overall because size seems to have some kind of impact on it. Or my nucleus could just be energized and you can just get rid of some excess energy. So here's plutonium 239. The plutonium 239 ejects an alpha particle. So this will be written as He, but it could also be written as an alpha symbol, sort of like a infinity symbol with one of the sides chopped off. And then the other part of this is what's left behind is this uranium-235. So where do these numbers come from? Well, 4 and 235 is 239, 2 and 92 is 94. So they have to add up. So that's why type 1 is still pretty useful, because you can see those numbers changing. So what's happening with the beta decay? Here I've got carbon 14 in all of us. There's too many neutrons for this number of protons for that size atom. So it wants to get rid of it. And so it does. What it does is it shoots an electron out of its nucleus. So one of the protons turns into a neutron. And so I've got 7 plus minus 1 is 6. 14 plus 0 is 14. Okay with that? Okay. So really what we're talking about is the nucleus's proton number changing through various methods. We got some other stuff that can happen. We've got positron emission. We've got electron capture, and we've got neutron emission. So the neutron emission is kind of easy. It just shoots a neutron out of itself. The electron capture, so the closest electron to the nucleus gets grabbed by the nucleus and attached to a proton. And now my proton number goes down 1 and my neutron number goes up 1. So it's able to reduce whatever the element is, it's able to reduce its proton number by 1. And the last one, what is that? What do you think that word sounds like? Positron.
It's the.
Yeah, positron, electron. It's a positively charged electron, which exists.
fan.
You're not a fan? We actually use it in PET scans. PET scan is a positron emission topography. So it's sort of like the problem with X-rays is you can't really study soft tissue because the X-rays just pass through it. You get like some graying, a contrasty color change, and really good radiologists can like pick up stuff like that. But you're probably gonna, if it's a soft tissue injury, you're probably gonna get an MRI, or you can get a PET scan. So we can produce positrons, and those positrons go in and they cause damage, really, and then we pick up on the damage. Okay, so I'm just going to breeze through the whole light radiation thing, because that was part of Chemistry 121. But when we talk about light, we need to make sure that we need to remember that this is a type of radiation. Most of it is non-ionizing, but regardless, it's still radiation. So we're all being exposed by light, and we're not worried about it, because any photons of light with an energy level less than UV light cannot break a carbon-carbon bond. So cannot cause cancer. Cancer is caused by the breaking of carbon-carbon bonds. And if the thing can't break the bond, the thing can't cause cancer. So visible light can't cause cancer. I don't think any of us are afraid of, a light bulb or a flash. None of us are afraid of the heat that comes off of our stovetop. But we do have people being afraid of the microwave oven and of, say, cell phone radiation. And why are those things? Why should they not be concerned about those things? Because the thing that can cause cancer is here. These things on this side. So we've got X-rays, gamma rays, ultraviolet. So if I take this and I move myself down here, this is frequency, and then the bottom one down here is energy of 1 photon in electron volts. So I go straight down, electron volts is about 10. So you have 10 electron volts, 10 to the 1, for radiation. That's the minimum amount of voltage or energy that can cause that carbon-carbon bond to break. So obviously,
another kind of radiation of UV radiation, that's 100. There's 1,000, 10,000, 100,000, million. So it goes up a lot. But if I don't have at least 10 electron volts, I can't get that bond break. So if I'm backing off from this, visible light is right next to that one, but not on it. Here's infrared and it's at 1. Here's microwave at 0.1. So the strongest microwave is 100 times not powerful enough to break the bond. The weakest microwave is 10,000 times too weak to break the bond. So can microwaves cause cancer? No, they can't. They literally cannot break the bond. Then if you go over to radio, which is it's right here on the side of FM, which is where your cell phone is. There's your microwave oven at what is that? 100,000 times too weak to break the bond. And then your cell phones are here at 1,000,000 times too weak to break the bond. So can your cell phone cause cancer? No, it can't. It's like trying to throw a tennis ball at a brick wall and expecting the wall to break. I don't care how hard you throw it, but thing's not going to break. So no radiation unless no cancer-ish unless you get at least ultraviolet.
Talking about how light is a dual nature. So again, all of this stuff was in 121. All right, so here we go. So let's talk about some nuclear equations. So we already saw this one up top. This is what your body is currently undergoing, or what happens during radioactive decay of carbon-14. The carbon-14 itself is going to be inherent in anything that is carbon-based. So animals, plants on this planet are carbon-based. So they're going to have some amount of radioactive carbon-14 in them. And it can beta decay itself into nitrogen, which is a little weird if you're thinking about that happening inside your body, right? So I got a glucose molecule. The glucose molecule has carbon in it. The glucose molecule doesn't know that that carbon's radioactive because it's got 6 electrons and 6 protons. It doesn't matter what its nucleus is. And then all of a sudden, it spontaneously turns into a nitrogen. So obviously that glucose molecule breaks because carbon makes 4 bonds and nitrogen can only make 3. And now there's a beta particle running around inside your body for a little period of time, possibly causing havoc. But again, we're making sure that these numbers on each side of the arrow add up. So that's 6, there's 6, there's 14, there's 14. So let's look at another one of these. I've got carbon-14 being hit with hydrogen, and then it turns into regular old nitrogen and a neutron. But again, that equals 7, that equals 7, that equals 15, that equals. And this last one down here, this one's quite important to us. So there's 3 reactions going on in there. So the first one is a neutron inserting itself or being inserted into a uranium atom with the isotopic mass of 235. And for a moment, it turns into uranium-236, and then it splits apart into rubidium, cesium, and make sure we realize that there are 3 neutrons there. And so then what I've got is a proton number of 92, still have a proton number of 92, still have a proton number of 92. And I need to make sure that I've got 236 here, I've got 236 here, and 93 and 140 plus 3 neutrons over there gets us up to 236. So all of these things need to add up. I can't have any of the numbers not mesh. Does anybody know why this one's important? This is basically how we run nuclear power plants. So the nuclear part of the nuclear power plant is uranium-235. So that's kind of a problem. So periodic table, what's uranium's molar mass? Hmm. 238 and change, right? That's a problem because 238 does not undergo fission, which is what this is. Fission is a larger nucleus breaks up into smaller nuclei. So if I shoot a neutron into uranium-238, it turns into uranium-239. It doesn't do anything. But 235, when it gets hit and turns into 236, it basically explodes. So what's the problem with this? Most of the stuff on Earth has a mass of 238 and it's useless. What I need is 235. Why is that super problematic? Nope. 238 isn't going to decay into 235. It won't happen. There's no mechanism to go from 238 naturally down to 235. So we can't make it. The problem is uranium-238. How many electrons does it have? How about uranium-235? The same. So tell me about the chemistry of uranium-238 and uranium-235. It's exactly the same. I cannot use chemical means to separate them because they are the same atom. They're not the same isotope, but they're the same element. So that becomes a huge problem. So I say we, I mean humans, and more specifically, scientists that are in the United States realize that the only fissionable atom of uranium is uranium-235. And now we need to figure out how to get uranium-235 when it's about 1 out of every 10,000 atoms is uranium-235 and the rest is 238. I mean, there are a lot of isotopes of uranium, but it's mostly 235 with a smidge of mostly 238 with a smidge of 235 in it. So what could you do? The difference is their mass, right? So is there something that we talked about in Chem 121 at the end that we could use for this? I mean, don't feel bad. It took the smartest people on the planet to realize they could do this. It's a mass thing, right? So what I need to do is figure out a way to differentiate things that are chemically the same but have different masses. So what is something you can do kind of physicsy related where you can get things of different masses to separate out from each other? You can make them run a race. And if all of the things have the same amount of energy, what's going to happen?
The energy is the same.
The energy is the same. So Ethan and I are going to go run, I don't know, 100-meter dash. And we get to have the exact same amount of energy during the run. Who's going to cross the finish line first? How can Ethan and I have the same amount of energy? If he's going faster. How can a dump truck and a VW bug have the same amount of energy? Dump truck's moving slow, VW bug's moving fast. So in this analogy, I'm a dump truck.
No mass.
So the mass makes it force the thing to go slow. right? So what they did is they literally had them run a race. So what's going to come out of the race first? If they all have the same amount of energy, the smaller thing will come out first. So do we know what gas chromatography is? Do you remember the word chromatography from 121? Chromatography was this thingy. And we put some spots down on here. And then if you put it into a liquid and the liquid traveled up and it drug and separated things out, that's what chromatography is. You used a marker or something like that, right? You guys used copper, iron, and cobalt to separate those things out. So this is thin layer chromatography, and GC is gas chromatography. So we turn the uranium into a gas. So that was the first fundamental. Ooh, wow. Somebody said, maybe we can turn it into a gas. Can we turn uranium into a gas? And they're like, well, we have to heat it up to 2000 degrees. And they're like, that's not practical. So what a opportunistic smart chemist did was react it with the most reactive thing on the table. So what's the most reactive element on the periodic table? Fluorine. Reacted it with fluorine, and it made this UF6, which oddly is a gas. It's a really big gas, but it's a gas. So imagine that I've got a gas particle, and in one of them, the uranium is 238, and then in another one, it's 235. And those two things go into a tube. And they're at the exact same temperature. If they're at the same temperature, that means their average kinetic energy is the same. And their average kinetic energy is KE is equal to 1/2 mass times velocity squared. If this is the same for these two substances, and somebody's got a bigger mass, then the other thing's got to be moving faster. So they react the uranium, all the different isotopes of uranium with this fluorine, turn it into uranium hexafluoride, and then allow it to run through a gas chromatography apparatus. The tube is super thin, like, I don't know, 3 times thicker than a fishing line. But it's really long, really long. So eventually, the uranium-235 will make it out of the tube faster. So they'll use something called the mass spec, which is the device that will determine the size, the actual mass of different atoms or molecules that come out of a gas chromatography machine. And then when they come out, it'll say, basically it's a time flight thing. So here's my tube, right? And the tube has these things in it, both of these things in it. And then I've got this sensor here. And the sensor is, there's a couple ways to do it. Let's just say it's charged. So let's say that the sensor, doesn't really matter. These molecules come flying out, okay? And one of them flies that far. And another one flies that far. So which one's which?
35 further.
The 235 made it a further distance because it's lighter. It was moving faster in the tube. It was moving faster when it exited the tube. And this is 238. So what you can do is you can set up your gas chromatography with a mass spec. And so it's periodically sampling how far these things make it. And you're like 235, 235. And so there's a tank getting filled with uranium hexafluoride with 235 in it. And then the machine, the mass spec says, okay, some 238s are coming through now. 238s are coming through. So divert it to another tank. Does that make sense? So I got one tank filled with mostly 235, but not a ton. Because remember, it was like 1 out of every 10,000. And just the way that statistics work, some of these 238s are going to make it with the 235s. So now I got this tank and it was 10,000 to 1. And now let's say it's 1,000 to 1. So you do it again with this tank. And then you make it 100 to 1. And then you make it 10 to 1. Then you make it 1 to 1. And then you start going the other direction. So if you want to run a nuclear power plant
It only needs to be 9% 235.
That's it. And so all the commercial nuclear power plants on the planet are running at 9% uranium-235. The ones that the military uses are 90% uranium-235. They are much, much, much more expensive, but they also last like 30 years of constant full power use. So there's a reason you don't want to pull your aircraft carrier into dry dock for 6 months to change out its core, because nuclear power plants are usually changing out their uranium every 6 months. So you can't do that with an aircraft carrier. So ours supposedly was going to last more than 20 years. Okay, so can the nuclear power plant blow up? I guess you need to define blow up, because obviously we had one blow up in Russia, right? But and we did have one blow up in the United States. We will talk about that. We had one almost blow up in the United States that you probably have heard of before. Definitely haven't heard of the one that did blow up. But the issue is this isn't concentrated enough to actually mushroom cloud. This is 1,000 times less concentrated than it needs to be. So if I want to build a bomb, it has to be 99.99% uranium-235. That's hard to do. Does anybody know where this work was done? No, I haven't seen Oppenheimer. I'm guessing they talked about part of this, but they might talk about the other part too. Anybody see it? Do they talk about this? Or do they talk about the mechanism part? So there's two main places where the nuclear bomb was created. One was in New Mexico and Albuquerque. And so in Albuquerque, or not Albuquerque, Los Alamos. That's where they built the mechanism, the bomb thing, the thing that allowed the nuclear explosion to happen. So if you're looking at the nuclear bomb, that's the thing that they built. There's a lot of physics around. But the actual 99.9% uranium-235, that came from Oak Ridge, Tennessee. Oak Ridge is premier nuclear facility on the planet. It was run by element number 106, which is Seaborgium. So Glenn Seaborg is the person who was in charge of this part. It's not as, it's really just a bunch of people in a lab doing chemistry. And so it's not as cool looking as the Oppenheimer part, which is building the bomb portion of it. Just having this isn't even good enough. It's not good enough at all. So what I want you to do is picture a soccer ball, all right? So I put the uranium-235, I turn it into a ball, and then around the ball, I put hexagons and pentagons, just like a soccer ball, except those hexagons and pentagons are explosives, conventional explosives, like C4, okay? So the only way to get this thing to go nuclear is to have every single one of those hexagons and pentagons explode at the exact same time, within microseconds of each other. That in itself is a problem. Switches that are calibrated to a microsecond, you can't actually purchase one. They've been under strict regulatory control of the United States and the other nuclear powered countries on the planet. So people, this is an issue, creating a switch that can turn on and off at microsecond times. Because what I need is every single one of those soccer ball hexagons and pentagons to explode simultaneously. And what that does is the explosion is just the rapid expansion of a gas, and it takes the soccer ball sized thing of uranium-235 and squishes it together. It literally just pushes the atoms in closer. And that's where you get a nuclear bomb explosion. So you can't like shoot it or hit it with a missile or, you know, whatever it is you think you can do to it. It needs to be incredibly specific. There was a Peacemaker was the name of the movie. It had Nicole Kidman and George Clooney in it. And terrorists had got their hands on a bomb, a nuclear bomb. And they did a good job of showing what the bomb was. It was maybe cantaloupe size, but it had those little hexagons and pentagons on it. And it was about ready to explode. And George just shoved like a pocket knife in between a couple of those pieces and popped one of the pieces out. And so now when that thing exploded, the explosion happened from all of those little pieces, and the uranium-235 squirted out the hole where he had popped that one out, and no nuclear explosion happened. Does that make sense? You need all of them to simultaneously compress the thing into an incredibly dense sphere, and that's the only way to get this to explode as like a mushroom cloud kind of thing. So how do we know this? That equation right there. Where'd this equation come from? Leibniz-Meitner. So this lady here. I have a picture of her. Oh yeah. I think we talked a little bit about it. Liz couldn't get a foothold in science, in the upper echelons of science, even though she was one of the smartest people on the planet, because, you know, she's a woman. And we recognize it, that guy there. Last question on the last exam. Boltzmann. So Boltzmann talked to her and said, "Oh, you're smarter than everybody, all of my grad students. You want to come work for me?" And they like gave him a hard time about it. And he was like, "I have an equation named after me. Who are you?" I quantified entropy. Who exactly are you? She can work for me because she's smarter than you. That's why she's working for me. And so he gave her the freedom to do what she wants. And her story is one day when she was drinking martinis with Enrico Fermi, who was probably in that movie, at near the University of Chicago, she wrote down something on a cocktail napkin and fell asleep on it. Then took it to work with her the next day and was like, "I think this is it. I think this is how we do nuclear power." And so this is the equation that she wrote down on that cocktail napkin after a few martinis. And that's the thing that we're still using today. And that's what blew up Hiroshima and Nagasaki. And is running 20% of the electrical grid in the United States and like 90% of France. Okay. So transuranium. What's the prefix trans? No, I'm thinking about it. It's sort of changed in recent years, right? In recent years, it meant like a gender change, but that's not the meaning of the word trans. Can you use it in any other context, that prefix? Okay, that's not bad. The transmission converts one thing into another. So maybe that's more of the genderish, but the other prefix meaning is sort of like transatlantic, transcontinental, meaning going across. So what we mean here is past uranium. So what are the elements that are past uranium? And so anything past uranium, that's transuranium element. We have made all of those elements. We think maybe plutonium can be made naturally if it's in a high enough concentration of uranium. Like the uranium's natural decay can bombard itself enough to create some plutonium, but we're not 100% sure about that. But all those things after uranium, so neptunium, plutonium, americium, all of those things are the transuranium elements that humans have made. They almost all have no use. Plutonium obviously has a use. You can make a bomb out of it. You can power a nuclear power plant with it. Does anybody else know what the other use for plutonium is? Old pacemakers or batteries. They're really, really good batteries, like 10-year, last for 10 years kind of situation. They decided it was better to put a pacemaker with a plutonium powered battery inside of a person than change the battery out every X number of months or years. Like that surgery was going to be too much of a pain. We've got other ways to deal with that.
And some really cool stuff is coming shortly, especially for the pacemaker people. We also, the probes that we send off into space, deep space probes, they have solar panels on them, but they also have plutonium powered batteries because we're not worried about exposure out there. Since you can't get worse exposure than being in just straight space. That's probably something we don't know. You can't really hang out in space. Like obviously you need a spacesuit, but there are very specific circumstances that allow a person to actually be in space. And most importantly is you can't see the sun. Like if you're being exposed by the sun, you're being bombarded with a ridiculous amount of radiation. So when they do spacewalks, they try to do them when International Space Station and the shuttle are on the backside of Earth where they're shadowed because they don't want to die, be blinded. That's probably the scariest thing about going to Mars is how are you going to deal with, like, did any of you guys see the Northern Lights?
Missed them.
So did we. We missed them too. Well, my brother was in Gresham, got ridiculous photos. But what was that caused by? Solar flare. Solar flare will, if there was anything scheduled to be outside the space station when the solar flare was seen, they got their asses right back into there because you would literally be boiled. The reason that the atmosphere had northern lights is because there was so much excess radiation in the atmosphere. There were literally electrons were flying off nitrogen, oxygen, ozone, and then crashing back down and producing those different colored lights. And if that had hit a person, they would have just caught on fire inside their suit. Their blood would have boiled. So that's a long, several-year trip to Mars. And so you got to have an incredibly good protective capability, but that's a problem, right? How much stuff can you put on the ship? Because you got to speed it up, but then you got to slow it down, and that's a lot of energy to do that. So it'll be an issue. Okay, so let's talk about some field effects. So let's look at this first drawing here. First off, you can easily find a radiation source that will produce alpha, beta, and gamma all at the same time. So what I have here is basically a lead block with a chamber inside of it and a portal to allow some of the radiation to leak out. And so what we've done is we've allowed it to go down through an electric field. So basically a capacitor where there's a positive plate and a negative plate. I mean, you could literally use jumper cables off of a car for this, although maybe the 12 volts is probably less than you want. But regardless, why does the beam split into 3 parts? Gamma's not charged, so it just goes straight on through. Neutrons would also just go straight on through because they're not charged. Is there anything else to notice about the path? It is the beta. There's a larger deflection, right? So there's a couple of things going on there. One, the beta has a really small mass. Its mass is about 7,200 times less than the mass of an alpha particle because it's just an electron and the alpha particle is 2 protons, 2 neutrons. But the alpha particle has twice the charge. It's got a +2 charge and the electron's only got a -1 charge. So the deflection isn't quite as much as you might expect because of that difference in their charge. But the beta will absolutely turn a significantly larger, you'll have a significantly larger deflection out of the beta in the same way the VW bug and the dump truck, the VW bug can take that corner better than the dump truck. And this is how the traditional cathode ray tube televisions that maybe your grandparents still have work. They shoot beta particles, and then we use electric fields and magnetic fields to direct the electrons, because that's what's hitting the inside of those TVs is electrons.
So same kind of situation happening here with this magnet. So it's just a, graphical display of a plain horseshoe magnet. We've got an alpha particle on the right. I got a gamma going right through the middle, and on the left, I've got a beta particle. So the beta particle is going to turn a lot more because it's lighter. Even though its charge is only one, but it's going to turn one direction, and it's going to be the opposite direction for the alpha particle because they're opposites in their charges. So this is how we can control radioactive particles to use them for different purposes. So I'm just going to say sorry. I don't have any control over this. Remember when I put the units up for gas pressure at the end of chapter 9 at the end of 121? There was like 8 different gas units, PSI, torr, inches of mercury, inches of water, bars, kilopascals, all those different things. Same kind of situation here. Got a bunch of different people coming up and doing research on a bunch of different stuff. And so a bunch of different names come in. So somebody's name, somebody's name, somebody's name, somebody's name. And then we'll talk about those things in a second. So the first one is called the Becquerel. Henry Becquerel was one of the first people to discover radiation. And so the unit that they named after him was equivalent to 1 nuclear disintegration per second. So I got something that's radioactive. Radioactive thing decays 1 time per second. That's a terrible unit because when these things radioactive decay, we'll look at the last unit. Read the definition of a Curie. So we shouldn't be talking about a decay per second. We should be talking about billions of decays per second, because that's what happens. So there's a rock called pitchblende, and it's just an ore that's got a lot of uranium in it. And that would have billions of disintegrations per second from that rock. So this first one, nobody really uses the Becquerel because the number would have to be too big. So the next guy is William Röntgen. And so he comes up with 2 different definitions for the unit, depending on what the situation is. So William was, again, one of the first people to discover radiation, and he was super funny. His wife was into photography. Photography was fresh. Like, people were just understanding that a person can do it, how it works and whatnot. And so she had him pick up some photography paper, some basically like a negative. And he went and bought it, and he put it in a drawer. And then somebody came in and handed him a sample of this weird rock that seemed to glow. And then he put it in a drawer and forgot about it. And then went back and got grabbed his wife's photographic paper and gave it to her. And then, she did her thing. And like a week later, she went to him and was like, "Why did you take a picture of a set of keys with every single one of those?" He's like, "I don't have a camera. What are you talking about?" And she went to try to use the photographic film, and it was already exposed with a set of keys, every single one of them. And he's like, "Let me look at it," looks at it, and he's like, "Those look like my lab keys." He had put the photographic paper in the top drawer of his desk. His keys were in the center drawer of his desk, and in the bottom drawer, he put this rock that seemed to glow in the dark. So he had just realized that this glow in the dark rock was able to penetrate wood, multiple layers of wood, but it wasn't able to do what?
Not the film or the photo.
It wasn't able to penetrate the keys, right? So all of the photographic paper was exposed, except where it tried to get through the keys, it was absorbed there. So he discovered this radiation source, and at that point, they're like, "All right, well, is this anywhere else?" And as soon as these guys discovered that it was a thing, I mean, obviously it had been here this entire time, we started looking for it. And we're like, okay, so what could we use? Well, you can use photographic paper, and that will, immediately tell you can put it in a dark room. And so we started finding things that were radioactive. So his 2 units are, I don't care about the
the decimal numbers, but it's 10 to the 9th and 10 to the 12th. So what's the difference between those two things? 3 orders of magnitude, 1,000. Okay with that? Moving the decimal place over 3 spots.
All right, so this is ion pairs in dry air. This is ion pairs in tissue.
So what did he do? He had this radiation source and he literally put it in a box with some air. And then he was measuring the charge of the air. So this radiation source was going off, hitting oxygens and nitrogen molecules and literally splitting them and creating an electric field. And so he was able to quantify how many times per second these ion pairs were created. So if this happens, what ends up happening with N2, one nitrogen goes and the other nitrogen goes the other way, they don't have the same number of protons or electrons on them. So one's a cation and one's an anion. And with a large electric field, you can separate them out and you count them.
So what he found was about 2 billion pairs of would be created in dry air. Why is it 1,000 times more in
A piece of chicken.
it's solid? Because the density is about 1,000 times more. So you being exposed to radiation is going to be 1,000 times worse than the air being exposed because you're at 1,000 times more dense in the air. So we use this, and then the RAD value is radiation absorbed dose. So this is usually used on, as you can imagine, anything that gets exposed to radiation, things will happen to it. And so structurally, like a pipe being exposed to radiation will actually eventually break down. The crystal lattice structure is being pounded. And I know we discussed crystal lattice structures, and having different things embedded in the crystal lattice structure can increase strength. And so it increased strength, but then the rigidity becomes so high that any flexing in whatsoever, sort of like glass, and it can cause it to shatter. So you reduce the usability of things. So you can measure that with radiation dose. And then we've got a gray, which is the official unit for the metric system. And honestly, I've never seen anybody ever use it. It's weird, but even though it's the official unit, nobody uses it. I don't even have one of the ones up here that people do use, which is the Siemens. And then there's a Roentgen equivalent man. That's what the REM means. So this one is about like a beam or a pipe being exposed to radiation. This is specifically about people. Obviously, that's important. So that's the unit that on that in the Navy, that you wear this thing on your belt and they measure how much REM you were exposed to. So the difference is I take the RAD number and I multiply it by a quality factor. And the quality factor is dependent upon the type of radiation you get exposed to. So if you get exposed to gamma or beta, then the REM number and the RAD number are the same thing. The QF number is a 1. If you get exposed to neutrons, you're going to multiply it by 10. And if you're exposed to alpha, you multiply it by 20. So alpha is definitely the most dangerous, but exposure is really specific. So if I've got an alpha source and I'm holding it here, none of you should be concerned about it, because we'll find out that you need to eat it or breathe it for it to be a problem. It can't actually get through your body. And then that last one is the Curie, and that's based off of Marie Curie. And her husband had taken different types of radiation and done chemistry on these natural sources of radiation, and she actually chemically isolated radium. So radium's on the table there, the bottom of column number 2, and it was super useful. She was a remarkable person. Obviously, she's super smart for being able to think about all this stuff, but she was one of the first people to use radiation medically. So during World War I, she enlisted and was basically like a type of doctor, and she would go around to battlefields and use her machine. So take a piece of photographic paper, and then she would had her radium, that she's like literally the only person on the planet that has any of it, in her little lead box, and she would expose the person to it with the photographic plate on the backside, and we're like, oh, the shrapnel's right here.
and then the doctor can go in and pull the shrapnel out. So she was literally doing battlefield x-rays on people with her own portable radiation source with zero precautions. Hence, she died at like 54 of leukemia. All the exposure could have been from her lab work, could have been from her battlefield work, regardless. She was immersed in the radiation. So we named the Curie after her. Okay, so I want to talk about this. Yeah, let's do this part right here. Okay, so acute dose response effects in humans. So what's that acute word mean? The other word, the opposite of this one would be cumulative.
What, in one instance then?
So acute is boom, I got hit with it, and then now it's over. Cumulative is, I'm being exposed to a certain amount of radiation over the course of a year. I had 2 X-rays, a dental X-ray and a foot X-ray, and then had a CAT scan, and I went to Colorado, and all these different possible exposures that you had over the course of a year. Versus I got nailed with something right here. Okay, so here's a 1 millirem, so 1,000 millirem, which equals 1 rem. All right, so if you, and I'll put this in perspective, on the aircraft carrier, I never saw a number for a month bigger than 7. For the cumulative nature of an entire month, never saw anything bigger than 7. Even when I went into the reactor room, it shut down, but regardless. So here a person gets hit all at one time with 1,000 millirem. What happens? You can't really tell. There's a statistical chance that something can happen to an infant if while they were in utero, they were exposed. So why is that? Why is the in utero a thing? No, it's not about immune system. It's about developing. What's a fetus doing? Mitosis. Nothing but mitosis, right? So every single cell is undergoing mitosis. So every single cell, if hit by radiation, could have a problem. So we're not saying that the baby dies right away, the in utero baby. We're saying sometime during infancy, something could manifest itself. There's a slight statistical increase. So, but that's it. We haven't, if you got exposed to 1,000, it would be like, you wouldn't even know. You'd have zero idea that that just happened to you. And we have no way of knowing if that happened to you or not, because it's a light that was turned on and turned off. This is like gamma or X-ray exposure. Okay, so 10,000. So now we're 10 times more radiation. And the effects, again, they're hard to measure. And again, what we're talking about is an embryo. So what do you see around every single X-ray sign? Sorry, around all X-rays, there's a sign that says what? Come on, infer the sign based off of the first 2 things we talked about. I suppose it's not a huge deal for you 3, but you. No. If you are pregnant, go away. Does that make sense? Right here with these first 2, the exposures are only talking in utero. So the X-ray tech will say to Veronica, are you pregnant or could you be pregnant? So it's not just are you, it's like, there's there a possibility you could be pregnant? Because if that's the case, you got to get the hell out. They won't allow a pregnant person to be anywhere near this, because the last thing anybody wants is an infant with cancer. Okay, so Now we're 10 times bigger. We're at 100,000. We're at 100 rem you're getting nailed with, and you don't really know. Like there's no obvious effects. There's some tiredness to it. And you've got basically you got hit with enough radiation to kill enough cells to cause enough problems that your life will probably be a little bit shorter, but it's hard to tell exactly how much shorter your life's going to be. Once we hit the million, though, now stuff happens. Death, really. You end up dying because you starved to death, which is a weird way to go from radiation exposure. But what ends up happening is all of the cilia in your small intestines dies and scabs over, and you can't absorb nutrients. And you might not know this, but you can't be intravenously fed for more than, say, 30 days. That's about the limit. Your kidneys will shut down, your body will shut down. If you've got, you might say, oh, wow, there's been people in comas for years. How do they deal with people in comas? Obviously, they're not, chewing. So how does a person who's been in a coma for a year, even though you can't blood supply feed them food for more than a month? There's a feeding tube goes up their nose, and literally a slurry goes up that's got fats, carbohydrates, and proteins in it. Basically, they're being fed baby food tube-wise directly into their stomach. And that what doesn't work for this situation because it's the small intestines that are absorbing the nutrients, and these things can't absorb nutrients anymore. Once we get to the 10 million, that's what people think of when they think, oh, I was exposed to radiation, like hit with radiation, just keel over and basically die almost immediately. There have been some, I mean, we definitely have some examples of this happening. Obviously, the 2 explosions in Japan, but we've got other exposures as well, most notably Chernobyl, which we'll talk about, and some assassinations as well. Yeah, that's definitely a thing with this, getting exposed to that much radiation. So the younger you are, the more damaging it is really what this works out to be. And for the most part, you couldn't possibly be exposed to enough radiation to kill you until you get exposed to very high amounts of radiation, which could happen. Well, I mean, it's pretty much impossible for a regular person to be exposed to this much radiation, into the 100,000 or into the million, or actually, when I think about it, any of these numbers. I mean, you would have to be, even to get the 1,000. I mean, do we know how the X-ray works? Like it's like that long, right? Okay with that? Like instantaneous, like the light goes through you and that's it. It's just that beep, and it's already turned off. So if you could stand in front of an X-ray machine for an extended period of time, you could get 1,000, but it'd have to be like an hour, like just constantly being exposed to it. This kind of thing actually did happen. There was a hospital that was demoed after an earthquake in Mexico, and this was like 35 years ago. The demo company had never demoed a hospital before, and so they didn't know that they were supposed to look for stuff. So there were a couple of X-ray machines in there. They demoed it, they threw all the stuff into a dump truck, and they took it to the dump and they dumped it. Well, there are some poor people in Mexico that rummaged through the dump, and like a 6-year-old boy found a shiny glow-in-the-dark rock, which was the X-ray machine's X-ray source. It was a chunk of cerium, radioactive cerium. So he thought it was cool, brought it home with him. Whole family got to play with it, thought it was great. The boy dies, mom dies, brothers and sisters die, and nobody knows what's going on. And they had to turn their entire block into, turn it all, can't live here anymore. The cerium exposure was so extreme that the house had to be demoed. They had to like dig up the house, the dirt, and get rid of the whole thing. So you could be exposed to these large quantities, but you'd have to have direct contact with the radiation source. And this was a man-made cerium source where we increased the purity of it, not just a rock that's got some cerium in it, but a purified form. Food,
It was, guy worked at the dump, found it and gave it to his daughter because he found it was glowing blue.
is that what it was? I thought it was
I
a
remember
stick.
reading.
Okay,
She called it for fairy dust and then everyone on the block got sick.
yeah, and then they all died. I mean, it had to have been fairly warm. Like, I'm surprised that it was touchable. Maybe it was an old source. Okay, so Fukushima happened. That was the Japanese earthquake and the power plant associated with that. And so, the mechanisms that maintain and operate the plant broke. We'll talk more about what broke specifically, but during that broke process, there was a time period where there was some flooding and there were some tanks that were exposed to the atmosphere. And what they needed to make sure didn't happen is that the flooding water from the ocean didn't come in and basically pull all of this radioactive water out of the plant. So they needed some people to go in and secure these things. And something kind of cool happened. The guys who used to work at the plant volunteered to go in. They were all in their 70s and 80s. Why did the Japanese government agree to this?
Because I remember if it was, they said something along the lines of, we're already old, it doesn't matter, don't make the guys do this.
That's like a nice, brave way to say it, but what's a more scientific way to be like, that's smart? No, not possible. Say that word again. No, not that word. You said it earlier. Why is the baby not supposed to be around the X-ray machine? Mitosis. They're 70 and 80. Their level of mitosis is as low as possible. So what are the chances of them actually, they're like, I don't want to die. I've got at least 10 years left in me, but my mitosis level is so low, the chances of me dying during this are small. But the 25-year-old guy, he's got a good chance. Plus, I mean, he's got gametes that he's probably going to use and make babies, and we don't want those things to be messed up. So they just send the old guys in and they took care of the problem. They reduced the amount of radiation that hit the ocean by a lot. Okay. Wednesday, we'll start talking about this inverse square law of radiation and exposure and whatnot. So go ahead and do what you need to do. I mean, even if you separate the copper out today and let it dry until Wednesday, you could do the mass on Wednesday after it's dry. And then the other lab is really simple, and actually we'll do it in here. It'll be cleaner. So I'll bring the stuff in you need for the other lab. It's literally simple.